Okay, let's talk about imaginary numbers. I know the name sounds like something out of a fantasy novel, right? But believe me, their power is incredibly real. We're going to uncover how a simple mathematical what if actually helps keep airplanes flying in the sky. Seriously.
All right, think about this for a second. The numbers you and I use every single day, they all live on a single straight line, right? The number line. But what if that was only half the story? What if numbers weren't just a line, but a whole plane, with a second, totally hidden dimension?
So let's get into it. Our journey here, it doesn't start with some super complex theory. Nope. It all begins with a deceptively simple problem. A problem our trusty old number line just can't handle.
And here it is. X squared equals -1. That's it. All we're looking for is a number that, when you multiply it by itself, you get -1. I mean, it seems straightforward, right? But go ahead, try it. Try any number you can think of. Positive, negative, doesn't matter. You'll pretty quickly find out it's impossible.
Yeah, think about it. A positive times a positive is positive, and a negative times a negative, well, that's also positive. So our good old real number line just offers no answer. And for centuries, that was pretty much the end of the story. Case closed.
But instead of just accepting no solution, some really brilliant, kind of rebellious minds decided to take this huge creative leap. They basically said, okay, if a solution doesn't exist in the real world, well, let's just imagine one.
And this is what they came up with. The imaginary unit, I. It's defined as simply the number whose square is -1. That's its whole job. So by its very definition, it solves the problem. It's such a simple, elegant fix.
And with this new number I in our toolkit, we can finally break free from that one-dimensional number line. We can start to explore a whole new two-dimensional landscape, the complex plane.
And this is how we visualize this whole new world? You see, we keep our familiar real number line, that's the horizontal axis, but now we add a brand new vertical axis for our imaginary numbers. So any number that has both a real part and an imaginary part, something like, say, 4 plus 2i, can now be plotted as a single point on this plane. It has an address, a location.
And just like that, poof, equations that were once totally impossible are now solvable. So what's the square root of -9? Well, that's just the square root of 9 times the square root of -1, which gives us plus or minus 3i. Problem solved.
Okay, so a point on this plane can be described in two ways. The first is Cartesian form, a plus bi. Think of it like giving directions. Go over this much, then up this much. But the second way, polar form, uses a distance and an angle. And let me tell you, this second way, that is what unlocks the true geometric power of complex numbers.
And this is so important because suddenly multiplication in the complex plane isn't just some abstract algebraic rule you have to memorize. No, it becomes this beautiful, intuitive geometric action. It's just a combination of scaling and rotation.
So in polar form, we're defining a point by just two things: how far it is from the center, that's r, or the modulus, and its angle, theta, which is the argument. That's it, just simple distance and direction.
You know, as one user on Reddit put it really well, it's this connection between polar coordinates and the exponential function that makes complex numbers so unbelievably useful in science. It creates this profound link between rotation and multiplication.
So how does it actually work? It's so simple, you're going to love this. To multiply two complex numbers, you just multiply their distances from the center and you add their angles together. That's literally it. You scale and you rotate. It is such a cool, intuitive way to think about multiplication.
Okay, so now that we get this whole geometry thing, we can start to see complex functions as these powerful engines of transformation. By applying these rules, the scaling and the rotating, to whole collections of points, these functions can literally stretch, twist, and reshape the entire complex plane in really predictable ways.
All right, let's try something. Let's start with a really simple shape, a circle. Every single point on the edge of that circle is a complex number, right? Now, what happens if we take every single one of those points and run them through a special function?
The function we're going to use is called the Joukowsky map, and what it does is, for each point z on our circle, it calculates a new point. And the formula is simple. You just take z and add its own reciprocal, 1 over z. This simple little bit of math creates this absolutely fascinating warping effect.
And what happens? This just brilliantly illustrates the power we're talking about. The function takes that simple, perfect circle and it reshapes it into an airfoil, the exact cross-section of an airplane wing. I mean, come on. That is a shocking and beautiful connection between abstract math and real-world engineering.
So yeah, this is way more than just a cool math trick. Let's look at exactly why this imaginary math is absolutely essential to making things fly.
And this isn't some newfangled idea either. The Joukowsky map has been a cornerstone of aerodynamics for more than 100 years. We're talking about the pioneers of flight using this stuff to understand and design the very first airplane wings.
Here's the secret to its power. You see, it's actually pretty easy to calculate the fluid flow around a simple shape, like a cylinder. The magic of the Joukowsky map is that it lets engineers take that simple, known solution and mathematically transform it into the much more complex and, way more important, flow of air around a wing. This lets them predict lift, analyze performance, and design more efficient aircraft. It's a game changer.
So at the end of the day, these numbers, born from an imaginary solution to a simple problem, they're not just some mathematical curiosity. They are a fundamental language for describing our physical world. From fluid dynamics and electrical engineering to the bizarre world of quantum mechanics, they are absolutely essential.
It really makes you wonder, doesn't it? The journey from a seemingly unsolvable equation all the way to the design of a modern jetliner was powered by one simple leap of imagination. So what other impossible or abstract ideas are out there, just waiting for us to imagine them into reality, waiting to unlock an even deeper understanding of our world?
Thanks so much for joining me on this one. I really hope you have a new appreciation for the very real, very tangible power of imaginary numbers.